This is learning objective 18. Learning objective 18 is to write electron configurations using the rules that govern those electron configurations. So there are 3 rules for electron configurations, and we've already talked about the shape of the atomic orbital, which is what the wave looks like for the electron. We have talked about how many electrons can be in each of the suborbitals, or the shapes that they can contain. We have talked about the principal quantum number, which is the energy level that each of the electrons are located in. So the higher the number, the further away from the nucleus it is, whereas the lower the number, the closer the nucleus is. And we've talked about how the principal quantum number relates to the rho on the periodic table. Okay. So there are 3 rules for electron configurations. Again, when we're writing electron configurations, we are trying to figure out how are the electrons being placed into the electron cloud. So how is the atom built on the outside of the nucleus? So how is it built up from the nucleus? So the first of the 3 rules is the Aufbau rule, which states that electrons fill the lowest energy levels first. So n equals 1 is going to fill before n equals 2, okay? Now, we can make a diagram for your orbitals. You have 1s and then 2s. 3 all the way to 7s. So if you layer these one on top of the other, the s orbitals over the p orbitals over the d and then the f. So it looks something like this. So again, I've layered 1s, 2s all the way to 7s, and then I've layered 2p all the way to 7p. And then I went from 3d to 6d because it drops off. There's no 7th D. There's no 7th orbital for D. And then I have 4F and 5F. So the way we travel through this is, again, the lowest energy is going to fill first. The 1s fills. And then we go to 2s. And then we go to 2p, 3s. And then we go to 3p, 4s. And then we go to 3d, 4p, 5s. And then 4d, 5p, 6s. And then we'll fill 4F, 5D, 6P, 7S. And then finally we'll fill 5F, 6D, and 7P. So that is how we kind of order this. So you just layer them 1 through 7S, 2 through 7P, 3D through 6D, and then 4F through 5F. Again, this corresponds to the periodic table. So if you go to your periodic table, you can see this, right? So like I have, this is row 1, this is the S block, 1s, 2 to helium, 2, row 2, s2 to beryllium, 2, again, p block over here, 1, 2, 3, 4, 5, 6 to neon. And then 3, row 3, S2, 1, 2 here to magnesium. And then 3, row 3, P block, 1, 2, 3, 4, 5, 6 to argon. And then we go to 4s, which is the 4th row. So 4s, 1, 2 to calcium, and then this drops down. So this is my D block, and it drops from 4 to 3 because remember n minus 1 is the D. So, and this goes all the way up to 10 for zinc, and then we go back to 4p6. Okay, and then if you get down in here, you are going to go through 4F and 5F because it's n minus 2. So this is row 6. So 6 minus 2 would be 4. Okay. So energy level 1 is going to fill before energy level 2. S is going to fill before P. So then you have Pauli exclusion principle. So the suborbitals can only contain 2 electrons with opposite spins. So if I have an s orbital, so an s orbital has 1 suborbital, a p orbital has 3 suborbitals. A d has 5 suborbitals, and an f has 7 suborbitals. So in this suborbital, I cannot have an arrow pointing up and an arrow pointing up. If 2 electrons are coming into the same space, they have the same charge, which means that they repel one another. They do not attract one another. They don't want to go into the same space if they have everything the same about them. So the way that we fix that is by saying, okay, well, if one has an upward spin, the other one has to have a downward spin in order for them to go into the same space. So that is Pauli's exclusion principle. So Pauli came up with this idea that the suborbitals can only contain 2 electrons, and they have opposite spins if they're going in together to the orbital. Hund's rule states that each suborbital will fill with 1 electron before a second electron is added. So this really only applies to like p, d, and f. So if I've got a p suborbital, like a p orbital here, and I've got 3 suborbitals within the p, because p can hold up to 6 electrons, so it has 3 orbitals that kind of have different positions around in the 3D structure. So when P is being filled, if you are putting in 3 electrons to P, so let's say that P is 3, you have 3 electrons that you need to add to the P orbital. 1, 2, 3. This would not be the way that you would do this. You would have to add 1 electron into each orbital before you go back and double up. Okay, so this does not work. This is a violation of Hund's rule. Okay, so that's a violation of Hund's rule. This is following Hund's rule. So you have to have 1 electron in each line suborbital in order before you actually double the electrons up. Okay, 3 types of electron configurations that I make you do in class. The first is an orbital diagram. The orbital diagram shows electrons as arrows that look like this. So one's pointing up, one's pointing down. And orbitals as lines or dashes. So if I wanted to write the orbital diagram for phosphorus, so phosphorus is right here. It is in the 3rd row. It is in the P block. So this is the P block. And it is 1, 2, 3 in to the P block. So that means that we would have 3p3. We know that phosphorus has 15 electrons. It's in the 3rd row. It's in the P block. So we're going to end at 3p. I know that my diagram, I know that it looks like this, right? And I'm going to stop here at the 3p. Well, I can go to my periodic table and find out how many electrons is in the P block for phosphorus. And that would be 1, 2, 3 electrons in the P3. So I can write that in here as well if I wanted to. So 3. So then I know that I'm going to go through the 1s, and then I'm going to go through the 2s, and then I'm going to go through the 2p and 3s, and then I'm going to go through the 3p. Okay. So then setting this up, I have 1s, 2s, 2p, 3s, 3p. And then I can write these guys on the bottom here. So this would be my electron orbital diagram for this. And then I plug in the electrons. So I know that S always has 2 electrons. So 1, 2, and they're always going to be up and down. Now, when you go through the P, as you noticed, I was going through 1, 2, 3, and then I was doubling back up. That is due to Hund's rule. Remember Hund's rule, you've got to go all up and then down, or all down and then up. It doesn't really matter which way you do it. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 15 total electrons there. That's the orbital diagram. Like the long form configuration has the general form of 1s, 2, 2s, 2, so forth, and so on. So for phosphorus, again, we're going through 1s, then we go through 2s, then we go through 2p, 3s, and then we go to 3p. So 1s, 2, because there's 2 electrons in the s orbital. 2s, 2, 2p, 6, 3s, 2, 3p, 3. Now, the number in front represents the principal quantum number n. The s is corresponding to the shape of the orbital. So s is sphere, p is dumbbell. The exponent up here is representing the number of electrons. Okay, so then if I wanted to find out like what element this is, I would just need to add up the electrons as long as it's a neutral atom. So 1, 2, 3, 4 plus 6 is 10 plus 3, 2 plus 3 is 5. So that's 15 total electrons. So then I would know that if this is a neutral atom, then it's going to be phosphorus. Okay, so the noble gas configuration, which is the last configuration that we talk about in this class, is the short form, is what I call it. And this is the last noble gas symbol passed in the periodic table in brackets. And then you add the electron configuration to the element. So like whatever electron configuration is left over after you pass that noble gas is what you would write. So the noble gas is just, the noble gas in brackets is taking care of whatever the electron configuration of the noble gas. So in order to figure out what noble gas goes into the brackets, this is one row up from the element you want the configuration for. So remember that the noble gas is in group 18. So again, going back to phosphorus, what we're going to do is we're going to go up one row and all the way over. Well, that's neon. So neon would be in brackets. Now, what is the neon in brackets taking care of? Neon's configuration would be 1s2 to helium, 2s2 to beryllium, and 2p, 1, 2, 3, 4, 5, 6 to neon. So then all you have to do here is put neon in brackets, Ne. And again, this is taking care of like 1s2, 2s2, 2p6. So all of that's being taken care of. The leftover part to get to phosphorus is what we have to write. So after neon, we go through 3s2 here to magnesium, and then 2p3 to phosphorus. So then we can write 3s2, 3p3. Now, something really neat about this particular configuration is it's giving me the valence electrons. This would be considered my valence electrons. Anything after the neon would be considered valence electrons. Now, when we get into the d orbital that's a little different. So that is learning objective 18, to write electron configuration using rules that govern them. So again, the first rule is that the lowest energy levels fill first. So 1N comes before 2N. And it travels this way. So you go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. Pauli exclusion principle. Suborbitals can only contain 2 electrons with opposite spins. So in order for the electrons to come into a suborbital, they have to have something different about them. A violation of Pauli's exclusion principle would have the 2 arrows pointing up or the 2 arrows pointing down. That's a violation. They have to have 1 arrow up, 1 arrow down. And then the third rule is Hund's rule. Each suborbital has to fill with 1 electron before being doubled up. Pauli's exclusion principle and Hund's rule are really for orbital diagrams. So when we're talking orbital diagrams, that's where we're going to use Pauli's exclusion principle and Hund's rule. Your regular electron configurations follow the off-bow principle. So just make sure you are following that. Again, follow the method of how you go through 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. You can remember this, it will help a lot. Okay, so that was learning objective 18, write electron configurations using rules that govern them.